Hello, Lila. All right. Hello, Raymond. All right. Hello, Samaya. All right. Good afternoon, Danielle. Good afternoon, Luis. Hi. Wait, I'm starting. Okay, it's all right. Now it's all happening. Oh, and there's Michael. Awesome. Hello. What I say? Hello, Samaya. What? And then it's all happening. Blah, blah, blah. Hello, Samaya. Good afternoon, Danielle. Good afternoon, Luis. Hi, Montserrat. Hello, Sophia. Good afternoon, Jadith. Good afternoon, Abdul. Hello, Tania. Oh, hello, Sophia. Awesome. Oh, awesome. There's got to be a portal for like a two-handed. All right, that's awesome. Um, Wait, someone's going. Who else? And hello, thank you, Jadith, for the avatar. Thank you, Mantra, for the avatar. Oh, I'm good. Thank you, Nico, for asking. What great concern. I'm too. How much time do you have for me to really answer that? No, I'm good. Thank you. That's Shen, hello. Who else did I not say? If I didn't say hello to you, it's not, remember this. Oh, hello, Mantra. Oh, that's like Mantra just evolved from, wow, from an avatar to a video. It's like Eevee going to Espeon. All right. Good afternoon, Joyce. Awesome. Good greetings, Shen. Awesome. Okay. Now we're talking. And right, this isn't right. This okay, we all get this. So it's less and less time on that, more and more time on physics. Awesome. We're all here. Great. Again, we're gonna get into more and more physics now. You can stop me anytime. It is about you, not me. We hope, we want. So really, even if I'm going down something, if there's something that I've said I was going to say today or something, like definitely stop me. Who else is that? So, so right. So there's the board. So a little bit of bookkeeping, and then I mean, the main thing of today and for the next couple of classes, we want to start making our way through the physics of homework one. It, as I may have mentioned, homework one is sort of like transitions us from classical mechanics, physics 203 or physics 1. It transitions us from topic that is in principle part of physics 1 into the issues that are uniquely physics 2 or 204, right? So from the beginning to the end, we in principle transition from classical mechanics to the topic of harmonic oscillation. If you want to look it up in a book or look it up on a Khan Academy video or whatever, like the topic that we are getting into with all this is called simple harmonic oscillation. That's the first subtopic of physics 204. So homework one is meant to get us there. Um, as I've mentioned, we stay on homework one for a while because it establishes all these like equations and ideas that we need sort of for a lot of the course. So we're going to stay on homework one for a while, i.e. in a couple of minutes after announcements or questions, I'll be continuing to walk through solutions to homework one. See, I keep saying homework one, I mean homework 1B, right? So I'm going to continue a thing on a spring. I'm going to continue to be moving through solutions of thing on a spring. Again, you can stop me anytime. But what that means is as far as homework 1B is concerned, there's still plenty of time for you to do updates and revisions. Everybody's still in a position to get all the remaining points on it. It may take a while. For example, the very last question is almost impossible that anybody would really know how to do the last question honestly. So it's like almost impossible to honestly get all of the points on the last question, like right off the bat. But as we get closer to that, anything I say that's helpful, so it's still totally time to do revisions or 3 revisions or whatever until you get all the points on homework 1. If you turned in your first draft a little bit late, or you still haven't turned in a first draft, then maybe you don't get all the points. Like that's the one, you got to turn in a first draft like when it's due. But you still can get a ton of points even if you haven't done it at all. I hope that's clear. So I will let you know when I'm no longer accepting stuff. We're nowhere near that. That's number 1. Number 2, it's possible many of you may have just gotten back a draft with some amount of points, but with no feedback. Like I forget what category. There's a number of you that just got back a draft with a number but no feedback. And I apologize for that. The reason for that is hopefully I mean, I did it very quickly. I want you to see where I don't want to fall behind any more than you do. So if you didn't get all the points, but you didn't get feedback, hopefully you're going to see today in the class, hopefully you'll get a clear idea from the end of the class what's still missing in your homework or what could be improved. But if you don't see that, and usually what it means is the steps. Like it's very possible to get all the points on this homework with a number of answers wrong, but it's not possible to get all the points if you don't do all the steps, even if all your answers are right. So when in doubt, if you didn't get all the points, it probably means I need you to do certain steps more frequently or more correctly. And you'll see that again as we're talking through class today. But if by the end of the class, if you got points, but you didn't get feedback and it's still not clear why, what's missing or whatever, or you might just know it in your heart, but if it's still not clear, obviously send me a text or an email or whatever. That's number one. Number two, realize that the clock is not going to stop tonight or something. You still have plenty of time. So again, it could also come up next day in class. Number three, if you're ever very confident, if you ever think, wait, I think he graded this too fast. Like I actually think I have everything here. I've now listened to all of class and I think I have everything. You can always just like literally upload the draft again. If you're confident that something's wrong or that you just are owed all the rest of the point and I went too fast, you can upload the same draft again, and that'll notify me that you're sort of like almost like you're signaling me like, wait, I feel like you owe me the rest of the points either because I did do everything or just because like, where's my feedback, yo, prof? So when in doubt, if you don't get feedback and we're moving on, you could just upload the draft again and be like, wait, what happened here? And at the very worst, I might just give you the rest of the points if it comes to that. Okay, so hopefully that's clear. But probably at this stage, if you didn't get all the points yet, either in your heart there's still certain questions that you haven't answered, or there's steps that you still have to fill in, and there's plenty of time to do that. Okay, so that's on that. That's on 1B. 1A, unthingy things, I want to reiterate, that is more creative, exploratory. You don't have to do the 5-step method for that. You just have to clearly do on a separate sheet. You just have to make it clear what you're answering where on a separate sheet of paper. As long as you do it thoroughly and clearly, you'll get all the points, or certainly as long as you hand it in the first draft on time. So if you still owe me 1A, please do that. You don't have to stress it. Or if I owe you, let me know. But as far as like, why did I even assign homework 1A? What's that about? We're going to take a pause probably in the next class period, probably Wednesday, maybe next Monday, where once we've established enough of the equations and once we're rolling with enough of the mathematical physics that we have to get established here in homework 1, then I'm going to pause and take a left turn and back up and tell you why you did homework 1A. In other words, homework 1A is really supposed to be an introduction to what's the purpose of all this material. Oh, someone's here, sorry. Whoops, sorry. Okay. Homework 1A is really ultimately to lay the groundwork of what makes physics 204 different from physics 203. Like, where is this mass on a spring problem actually heading? Where are we trying to get to with all this? So once we've gone into it enough and we've got enough of the actual physics on paper, either as of next class or 2 classes later, then we're going to pause for a minute, even if we're not done with it. We're going to pause for a minute and talk about homework 1A and why that was assigned. But again, you should get all the points of that without stress. Okay, so in a second, if there's no questions, whatever, we're going to turn back to homework 1B. And so lastly, sorry. So lastly, if you're wondering what that all means in the end is there's nothing new due for a little while. There is no homework 1C, or well, for a little while. Actually, wait, let me check again. Wait, homework 2, let me check for a second. Homework 2, maybe if you know offhand, you can tell me, but I'm checking right now. Homework 2 is due.
It's due next week, Wednesday.
Yes, thank you. And you're absolutely right. And sorry, who was that? Sorry, who that was? Was that Mike?
There.
Oh, that was Raymond. Okay, Raymond, thank you. So you get points for that, blah, blah. But yeah. So homework 2, thank you, correct, is not even due till a week from this Wednesday. That's on purpose because okay, so don't worry about that yet. Really worry about trying to figure out where maybe you still could get points on homework 1B, or as I start now talking about the concepts for homework 1B, you're going to notice for a while I'm doing concepts that in theory are from calculus and from physics 203 in theory. But I know that you know that I know that you know that the concepts I'm about to go into right now could at best be very fuzzy. For like maybe depending on who your instructor was or whatever, maybe you didn't even see them at all. Or maybe you saw them a super long time ago or whatever. Like, so I'm gonna start showing you now the concepts that we need for this class. This is not a time for you to go, oh crap. Like, oh, he thinks I know all this cold and I totally don't know. I don't think anybody knows anything cold. I'm highlighting to you now what we need to know. So over the next week before you do homework 2, it's kind of an opportunity to now you'll realize what you need to know. So go back and find your notes from calculus class or from physics 1, blah, blah, or go to Khan Academy or go to my old videos or whatever and start refreshing yourself on the concepts that we're about to sort of lay out right now. So I'm technically reviewing them, like whatever. I'm going to strike a balance of like telling you what in principle came from old material, but like let's get ourselves up to speed on it now. Um, but yeah, okay. So I'm going to turn the so I'm about to turn the page. I'm going to start what I believe is I'm going to redraw the diagram. Well, oh yeah, and it's being transcribed. That's fine. That's great. Yeah, I'm going to redo the diagram and I'm going to start with question. I believe we've already done a full step method for question 2. So I'm going to start, for question 1. So I'm going to start with question 2. I'm going to start with doing the step method again, but I won't always do that. Sometimes I'll just give you answers. But right now I'm trying to guide you, so I'm going to do it with the step method. You can ask questions at any time. Just let me know, just right now, could you, if, I want to pause. Are there any questions at all about like where we've been or what we're about to do or like what's going on? Because I'm sure I forgot to say so. Are there any questions of any kind about the? Mhm.
Yeah. I have one question,
Yeah,
Professor.
yeah.
So for homework 1B, when is the final time to do that? Like when is the updated date?
Oh,
Like the due date?
for revisions of it, for like new uploads of it, or for the original?
Yeah.
For that right now, honestly, it's infinity. Realistically, probably I would stop taking revisions on that. Um, maybe 2 weeks from now. But honestly, like, okay, I will keep taking them. I'm not going to, as long as you handed in a first draft when it was due, then you could still potentially get all the points like for even 2 weeks from now. And if I literally am sick of taking them, or if I'm done, I'll explicitly tell you on that day that I'm no more and I'll put something in the Google. But the real thing is that homework 2 starts to be due a week from this Wednesday. So realistically, if I were you, I would encourage you to try to have homework 1 put to bed before you move on to homework 2. So realistically, you might want to try to be done with it with revisions before a week from this Wednesday. But certainly you can take that long and that's fine. Does that answer? Does that make?
Yes. Makes sense. Thank you.
Okay, thank you. Awesome. Um, Okay, awesome. Great question. And you could submit for points for closing a loop, blah, blah, or closing. All right. So I'm going to move on. What? Someone's here. I'm going to move on. I'm going to set up the next screen. And again, if you take a moment, everybody now, while I turn the page, take a moment to think, are you clear of because we're about to get into physics here. So if there's an issue, please let me know. Here we go. Bear with me for 1 second. I'm just changing the view on the screen. Okay. Sorry, just change. So we're all good to go. Okay. So step three. So, right. So this is the question for question 2. There's a situation, there's a setup. The question is at the initial position at x equals x naught. What's the instantaneous acceleration, right? Like notice now, I'm going to get in. Okay. Well, notice it says A equals question mark. Like it doesn't say A bar. It's not asking average acceleration, like from here to there. It's asking acceleration at a point, right? So in order to so I need to know something about physics that says something about acceleration. Like how do I get acceleration in general? Well, especially I need in this context, I need to know something about acceleration, and the only information I have so far has to do with force we got last week. So it seems to me the one general definition in principle is one that, although we've never said yet in this class, is established in physics 1 or physics 203. Like one fundamental law of physics is Newton's second law of motion, right? So this is a law. So it's like true, and it's really a fundamental law. So it's like true in all of space and time, according to Newton's second law of motion. The sum of all the forces the sum of all the forces acting on some mass equals the instantaneous acceleration of that mass times that mass, right? I mean, that's like an awkward way of saying it, but F net equals ma is Newton's second law, right? So that's my GDP. What I'm trying to emphasize here, it's a little subtle, like let me put it this way. If this were physics 203, if this were your first physics class, I would say that as a rule of thumb, your GDP, there could be more than one GDP. There could be more than one definition or principle that you need for like a hard problem. But anything you put down as a general definition or principle, anything you put down as universal truth before you go on to solve the problem should be something that's been established as a universal truth, right? So if it's in a first physics class, it would have to mean something that was literally established in that class already, either written down on a piece of paper that was assigned or discussed in a lecture. Like literally, like we can't use truths that we haven't established. And that's not just an academic thing, that's a scientific thing. Oh, sorry. Wait, I'm gonna look at the chat in 1 second. Great question in the chat. Hold on 1 second. The whole point of physics is that it's supposed to start with self-evident truths that we all agree on even before we do physics. And then it builds logically, one step at a time, from those self-evident truths. It builds in complexity and in intricacy until we get to things that we didn't already know or didn't necessarily expect. We build from self-evident truths to surprises. So anytime we're making an argument or a derivation or solving a problem, we're only allowed to use truths that we've already established in order to produce new ones, right? So if this were a first physics class, I would say we only can write down truths that we've established in that class. Now, it's a little bit more subtle here because we're in a second physics class. So I feel entitled to put down fundamental truths that in principle we learned last semester. It doesn't mean that you've mastered them. I'm not assuming that, but I'm assuming they're fair game. I'm assuming that it's logical for me to make a new argument about a new situation based on old things that have been established. In other words, even if I'm doing an 19th century problem, I can use things that we've discovered in the 17th century or in the 18th century. So I'm saying Newton's second law, and I'm going to move on and apply that to the problem. But first, there is something in the chat. The challenge port, a good question, Samaya. So yes, so the challenge portion of the homework, the reason we call it challenge is I'm acknowledging it's super hard. It is super hard. It's the problem that actually then requires us to get into, like you couldn't do it just based on the math or physics that you had last semester. So it's the first thing that's getting us into the new material. So it's super challenging in that when you first look at this homework, I can't imagine that you can just do it. So there's no punishment for not doing it. But yes, ultimately, it's the purpose of the whole sheet. So ultimately, by the time I get there in the class discussions, then if you want to get all the points on the homework, then I do want you to provide a good solution to that. You'll be using stuff I say in class. It won't be cheating. So basically what I'm saying is it's optional to do it at first, but eventually you have to do it to get all the points. I hope, does that? Okay, great, thank you. And that counts as closing a loop. Great. Okay, so, but that again is why you have tons of time to do this. To go back to not Gabriel, to go back to, sorry, I forgot who, to go back to, I'm just trying to get you, to go back to Michael's question. Like honestly, even though I'm recommending that you have this all tied up before you do the next homework, if I haven't gotten to the last if I haven't finished the sheet, I can't say that you have no more time to do it. So you don't, so I hope that's clear. So you have plenty of time to get to the end. Oh, and I won't get there today. Sorry, that's my all long speech at the beginning of this class is there's nothing new due for a while. But similarly, understand we're going to be working on this for we're not going to finish this sheet today. And when we don't finish it, that's not a mistake or a misfire. Okay. Okay, so that's step 3, GDP. So now we go to step. Okay. So here's where we start applying the general truth to the particular situation. So I want to start by saying this. Okay, first of all, I'm being overly technical here, again, because I want to get all the concepts out and sort of secretly like review physics 1 a little bit. But like, so I can't imagine your homework would look exactly like what I'm doing here. But let's first establish F net equals ma, Newton's second law. The way I write it, I'm trying to emphasize it's a vector equation, and we really have to be careful about vectors in this class in particular. Like, what? Well, yeah, like in general, F net equals ma is a vector equation. What does that really mean to me? What it really means, if you're in a three-dimensional situation, it really means that 3 separate equations are true simultaneously yet independently. Like what a vector, and we're going to see, I mean, technically you learned this last semester, just quick. I keep saying that, I'm going to stop. But like if I say force vector equals mass times acceleration vector, what I'm really saying is that F equals m, that sum of the forces along the x-axis equals the mass times the acceleration along the x-axis, while at the same time, but utterly independently, the sum of the forces along the y-axis equals the mass times the acceleration along the y-axis, while simultaneously, yet utterly independently, the sum of the forces along the z-axis equals the mass times the acceleration along the z-axis. Like, to be a vector equation is to be a vector equation in three-dimensional space really is to be three equations, one for each axis, true simultaneously yet independently. Now here, there's only one axis happening. Like everything is happening along a horizontal line or the x-axis. So for starters, I'm sure you probably didn't do this in your homework. That's fine. I'm just alerting you that here I can get rid of the arrows. I don't have to get bogged down in vectors here because everything is happening in one axis. So there's one equation, okay? So fine. But then also I want to be very clear because sometimes people are very careless about F net equals MA, and it really does matter in physics. I also want to make clear that okay, just so to be like, and I don't care if you call it F sub S or F for spring force or F sub H for Hooke's law force or F sub E for elastic force. My point is Newton's law says add up all the forces acting on something, divide by the mass. That's your acceleration. You have to add up all, in other words, the law says the net force equals mass times acceleration, or the sum of forces, same, different words for the same thing. Here, there's only one force acting on the mass, and it is the force of the spring. So fine, for the left side of M, in other words, normally we'd have to make a whole free body diagram and like add up all these arrows. Here, if we make a free body diagram, there's only one arrow in the diagram, and it's the spring force. So, okay, so in other words, here I can say, supposed to be an S. Okay, the negative kx force exerted by a spring is what is equal is what's producing acceleration here, right? Okay. And here, I know I'm dragging this out, but here we already established that negative kx equals negative what do we say, 30 newtons? Yeah, negative 30 newtons. And m, we were told, is equal to 0.3 kilograms, right? So here, negative, oh, oh, sorry, I should have done, I'm sorry, that's all true, but wait, my apologies, I'm trying to be clear about something. Sorry, that's all true. You don't have to cross it out, but I want to put something in before, sorry. I want to put this first because one thing I want to show, again, your homework may not, you might have gotten it right and what you did doesn't look exactly like mine, that's fine. But I'm trying to use these easier questions to teach better habits, stronger habits. So you'll notice what I'm trying to do here is write down as much as I possibly can. I'm trying to do as much physics as I can before I plug in numbers. That's really what I'm trying to get across here. Any algebra, any trigonometry, any calculus that has to happen, first of all, would happen in step 4 always. But second of all, my highest recommendation that will get more and more important and possibly more and more annoying until you get used to it is save the numbers for last. Yes, part of step 4 is plugging in, but I would do the plug in as late as possible. Partly because you're going to see more and more of our physics this semester is good, where the numbers are going to start to drop out. more and more, we're just trying to solve relationships in general. So you really want to get used to doing the necessary algebra or trig or calculus, like without being able to visualize concrete particular numbers. So the acceleration up, so I rearranged to solve for the thing that I'm interested in, which is acceleration at that point, at the initial position of 15 centimeters. So I wrote this. Okay, so now I can say, and I know that negative kx equals negative 30 newtons because we solved for it in the first question, right? Okay, so okay, so I dragged that out a bit, but so my final answer, as many of you know, and many of you wrote, the final answer is negative 100 meters per second squared, right? I mean, I did the math. Okay. To be clear, and the answer is trying to say that is the rate at which this thing, the rate at which it is changing velocity at that one particular position. That's what it is. It's instantaneous acceleration. Okay, I guess I'm just gonna go. I mean, I'm gonna go on if that's okay. So that's the answer to question two. I'm not trying to imply that it's hard. I'm just whatever. You get my point. All right, so that's question two. You can always ask me to go back. I'm always happy to go back. So now question three. Okay, the diagram is the same, right? So I just do that, something like that. So that's step one. Then what's the question here? The question now is at x equals, I believe, tell me if I'm wrong, but I believe the question now is at x equals 0, what's the acceleration? So this very question already implies that the rate of acceleration is going to change. I mean, this would be a meaningless question unless so I think it is. So why? Because sorry, okay, I'm going to turn the page so I can write this before I forget. But if you want, tell me if you want me to turn the page back. I'm happy to do that. Just give me 1 second. Okay, I'm just writing this down. Yeah, okay. Hold on. I'm rewriting step 3. Like I'm using the same GDPs that we used for step 1 and step 2, like F equals negative KX and F net equals MA. But I'm trying to emphasize now. I'm trying to say something general about, make a general observation about the nature of the spring force before I go on and like apply to this question. Um, I'm trying to say that what F equal, oh, sorry, what, I don't know why these arrows are missing, sorry. To say that F equals negative KX, what that, like, again, F net equals MA means in general, whatever forces are acting on an object, you add up all those forces, you get the acceleration of that object. In other words, F net equals MA is the consequence of forces acting on, sorry. Oh, did I, wait, sorry, Jadith. Am I on the page you want? Sorry, I missed that, 340. Am I on the correct page for you, Jadith? Oh, it says thank you, I guess I am. Okay. But by the way, oh yeah, you go, okay. But by the way, again, just note what Jadith just put in the chat. He can should totally put that into the portal that says please go back. Like he's getting points for the fact that he's paying enough attention that he's asking me to adjust my where I am. Like, please know he gets points for saying, can you turn back? And then when it says, yeah, I got it, which acknowledges that we're in a conversation, he could put that, all that same thing, he could double dip it in the portal that says closing a conversational path. And by the way, on any time you ever submit anything to any game portal, if I just write double dip, exclamation point, that's a signal I'm saying to you, I think there's another, at least another portal that applies to this. Just take the same thing and find the portal and you get more points. Okay. So, because it's like really helpful to all of us. And same thing, if you told me to go faster now, if someone like, you're talking too much, can you please move on? I mean, say it politely. But if someone in the direct chat said, please move on, that goes in the please go forward portal. Okay. Anyway, what I'm saying right now, and again, technically in the spirit of review, but what I'm saying right now is F net equals MA means take all the forces, whatever they might be, friction, springs, gravity, whatever, tension, any forces that are acting on an object, add them all up together. The point of them is that they produce acceleration. However, if we want to look at individual forces, like how to calculate them, how to understand, they all work according to different definitions and different computations. So the particular force exerted by a spring has its own equation, F equals negative KX. I hope you see that's not a contradiction or a redundancy to net F equals MA. Like it's two different like scales, what we're talking about. But F equals negative KX. What it's really telling you, what I'm telling you now, even if you never got it in physics 203, or you literally never heard it in physics 203, F equals negative KX is Hooke's law for a spring. It applies to springs, to elastic materials. And what it's literally saying mathematically is if X for any spring is the distance between where the edge of the spring actually is versus where its equilibrium position is. If the equilibrium position, the place where the edge would stay if you put it there, right? The equilibrium position of a spring we call X equals 0. And wherever the edge of the spring actually is, we call X. If it's on one side of equilibrium, if it's extended, we call it a positive number. If it's compressed, we call it a negative number. So what this law, Hooke's law, is saying is, it's saying that a spring, the farther you pull it out, the harder the spring, the farther you hold it out, the harder the spring itself pulls to get you back to equilibrium. Like that is hopefully not too complicated or hard to understand, but it is meant to be interesting. Not all forces work that way. Let's get it straight right now. Like gravity near the surface of the Earth, if you hold a box, if you have a box of mass m right here at 5 meters above the table, the force that gravity is pulling the box down toward the table is mg. right? But if I hold the box up here, the force of gravity pulling the box down to the table from this higher height is still mg, right? Near the surface of the Earth, the force exerted by gravity is a constant force. The force of elasticity is the first force we look at that is not constant with respect to position. It varies as a function of position. That's like the point of it. The good news, so the bad news or the interesting news of the elastic force is that it's a variable force, unlike gravity, or even unlike friction, unlike other forces we looked at in physics 203. But the good news is it's as simple a variation as we could possibly imagine. Like that's why we care so much about elasticity. It's variation, but it's simplest possible variation. That is, it's linear. It's a linear function. And the slope of that straight line graph is K, the stiffness of the spring. So that's why we're going to get a different, like the whole point here is to recognize, okay, whatever the force was being exerted on the mass out here is one thing, but as we look at smaller and smaller displacements from equilibrium, smaller and smaller amounts of stretches, the spring is pulling with weaker and weaker amounts. By the way, this is why, like this is what it means to be a spring. It's harder to hold a spring here than it is to hold it here. That's why gym equipment is made of springs, like for example. So the force will vary from place to place. Therefore, the instantaneous acceleration will vary from place to place. So in short, so all of this is just, I'm making that clear in step 3. Again, am I saying that you have to write all of this right now in your homework? No, I'm not saying you have to. What I'm really saying is I'm using this homework as an excuse to review material with you, but also I'm saying as if homework is practice for exams. When you get to an exam, especially in the first few pages of the exam or the first few problems of an exam, like if the problems are at all challenging at all, you have to think about them at all. The more you can write that is true in step 3 GDP, the more you could put down that is generally true that somehow is going to be helpful to this problem, the more you're both showing me that you know what's going on, and the more you're getting a bunch of points before things might go wrong. And also the more you're setting yourself up for success. Sorry. So the more you can establish in step 3 GDP, the more you're helping yourself and me, especially in exam. Okay, sorry, Michael, question.
Yeah, whenever you go back to the last slide, right? Sorry. So it says still force, right? After A equals question mark.
Oh, still true. Sorry, it's supposed to say.
Oh, still true.
Sorry, yeah. So I'm just saying, I'm trying to say, a good question. I'm trying to say that I'm still using the same GDPs from like question 1 and 2, but I'm kind of pointing out that now they're sort of becoming interesting. Like it's the same GDPs, but because of the nature of these GDPs, we're gonna get different answer to the question now. Like it's the same concept we're using, but it's not the same question. I'm just kind of trying to say. Does that make any sense?
Yeah, and for where it says the elastic force exerted by is that identical spring?
Oh, sorry, good question. Ideal. It's meant to say ideal. Sorry. So sorry. Yeah, ideal. So I'll quickly, and maybe this is good question. Maybe I'll say this for notes. Like, so this F equals negative kx is Hooke's law. It applies to all ideal springs, which means springs that are well behaved. So what is that really? I mean, in other words, a spring can become really crappy. A spring can be very, very badly designed. And it can be very badly designed or very old and worn, and then it won't like obey this law so well. The better a spring is, the more precisely it would obey this law. What does that really, really mean realistically? It means the close. You could write this in notes if you want. When I say a well-behaved spring or an ideal spring, what I really mean is a spring that is, as best as possible, uniformly coiled like a uniform constant number of turns per unit length, uniformly tight, like a spring that is the same amount of tightness all throughout. You don't want a spring with like gaps or kinks or something in it. And then, weirdly, most important of all, to make a really good spring, we really mean a spring that is really long compared to the amount that we're asking it to displace. So honestly, and this again, if you're taking notes, if you can write anything time you write things down that are not like literally written on the sheet and you want to screenshot them and put them in the notes section of it, you'll get points. So what I'm saying right now, I can't fit in this sheet, but to be an ideal spring, what we really want is, well, I'll write it in this way, but you can explain to me in notes what you mean. Like what we really want is delta x to be much, much smaller than x. We want the amount that the edge of the spring extends or compresses to be tiny compared to the whole length of the spring itself. So the spring could be, so the compressions could be huge as long as the whole spring is really, really huge, or the whole spring could be small as long as the compressions and extensions are even more substantially small. But that's what I mean by ideal. Anyway, that was a longer answer than you wanted, but good question. The word was ideal. Okay, so all right, so I'm gonna go on. All right, so all of this is, I'm just being conceptual and reviewing. I think most of you probably know. So here, therefore, back to step 4. I'll just cut to the chase. Like the force exerted on the spring when it's at, well, I'll put it this way. Sorry. We're looking at the equilibrium position. So the force exerted by the spring onto the mass when it gets to equilibrium is necessarily zero, like F equals negative, like by the math, and also by definition of equilibrium. That's literally what equilibrium means, that the spring is not trying to do anything when you're at the center. So therefore, you could stop me. So step 5. Okay, quick sidebar or observation. So I'm saying the answer. I'm saying the answer to question 3 is the instantaneous acceleration of the mass at the equilibrium position is 0. Now I want to say that's by definition, actually. That's literally what equilibrium means. Equilibrium means what's balanced, what's equal is the forces. It means for any force in general in physics, I mean, in general, if something's in equilibrium, it means all the forces are balanced or there are no forces at all. Same thing. So it means that the net force acting on an object is 0. That's what equilibrium means. Therefore, necessarily, if a system is in equilibrium, the instantaneous acceleration of the system is 0. Now, the reason I'm making a big point about this, I'm saying in physics, the definition of equilibrium is instantaneous acceleration is zero. The reason I'm saying this is that's as opposed to what people often think. I'm saying not, that's not, I'm saying not. Equilibrium, and I'm making it really small because I don't want you to confuse it for the truth. Equilibrium doesn't mean no motion. You can be moving through equilibrium. You're about to find that. In fact, the very next question is all about that. Like the very next question asks us, what is the instantaneous velocity or speed? Like once we, if we, sorry, in the next question, we're going to let the mass go and it's going to start moving toward equilibrium, right? And then it's going to presumably get to equilibrium. And then the question asks, how fast is it going when it gets to equilibrium? And the answer is not going to be zero. The purpose of the question is to establish, like, when you can move through an equilibrium position, or you can be moving at an equilibrium position. Equilibrium does not mean no motion. Equilibrium does not mean no motion. What equilibrium means is no acceleration. It means no change in motion. So what equilibrium really means in English, again, you could put this in notes if you want to, like, I mean, what equilibrium, like people tend to think of equilibrium as like stable, static, like stillness. It doesn't have to be stillness. It means no change. So what equilibrium, the reason people think of it as stillness is what the equilibrium position is the place that if I put the mass there and walked away, nothing would happen. If I sat the mass at equilibrium, it would stay at equilibrium, as opposed to any other place where I put the mass any other place and it starts and I walk away, it will start moving toward equilibrium. But bottom line, things are always trying to move toward equilibrium, but that doesn't mean they arrive there and stop. They move through it at some high speed. Equilibrium means, okay, no acceleration, not no velocity. Okay, so that's question 3. Now we start getting, I see that we have 22 minutes. Yeah, we have 22 minutes. So now we're going to start getting into some slightly heavier issue. Hopefully that, again, the purpose of everything I just said right now was just maybe to review a little bit, maybe to show you how the step method works for things that are reviews. In my heart of hearts, I'm thinking you're a little bit more bored and clear, like it, at any given moment, physics class is either sort of clear and kind of boring, or it's kind of exciting but confusing and stressful. Like, or at least that was always my experience. It was like one or the other. Right now, I'm kind of thinking that for most of you, you're a little bit more in the it's clear and on board zone, which is fine. None of this was supposed to be like that hard or crazy, but hopefully now you can at least picture what a spring means, what the elastic force always is. Elastic force means directly proportional to displacement. So now we get it. So if it's not clear, I'm going to pause for a second. If it's not clear, definitely. Sorry. Wait, someone is in the direct. Oh, wait. Sorry, someone's in the direct chat. Someone asked me to go back and I totally missed it. Oh, God, it was like 20 minutes ago. Sorry, I don't know how I saw that. I missed it. Hold on. Oh, you're good. Okay, thank you. You totally just got points for the. Okay, cool. Sorry, I'll catch that. Like you can. I don't know what you can do next time, but okay. All right. So I'm assuming everybody's clear. I'm going to take a moment to turn the page. It's okay to ask a question now. Don't assume that it's not okay. But I'm going to turn the page and go to question 4. And by the way, I can tell you right now, we're not going to get to question 5 today, and that's fine. Like we'll get to question 4. Um, okay. Now, this is where we get into issues. Everything I was just saying. Okay, so first I'm just highlighting kind of what I said before. I'm saying for the GDP, the first GDP is F equals negative kx. That means, like we just said a second ago, the force is varying with every position. So the acceleration is not constant, right? Acceleration over here is not the same as it is over there. Like we just established that in our last two answers. Therefore, why am I writing that? Because therefore, any of our constant acceleration equations from physics one, like x equals 1/2 at squared plus v naught t, or any of those equations that have an a in them, which is how we sort of began physics, they're like super useful. They're still super true when you have a constant acceleration, but we don't here. So none of those equations are going to apply. So I'm um again, note the habit that I'm doing that's often really good for exams, especially when things start getting hard. If you don't immediately know what to do to solve a problem, it actually is information. It is, well, maybe what I just wrote was kind of a step four thing, but writing down what isn't true about the problem is often still quite useful information. Put it well, I'll get more into this later, but the very thing that might be confusing you about a given problem is often very worth explicitly noting. Like the issue of this problem is we can't just use constant acceleration equations, or we can't even use F net equals ma. I mean, same point. Like we can't use the methods we were just using. So what can we use? All right, what I'm going to do now, especially because, and this is what I always do here, because there's only 17 minutes left. What I'm going to do is I'm going to commit to making sure that we do this problem, that we get to the solution. So I'm going to give you the skeleton of the solution for this problem, and I'm going to get an answer. So I'm going to zoom out first. I'm going to do it as though I'm just going to do it first. But the truth is, I'm going to use concepts and stuff that I would imagine some of you don't fully remember or never fully understood from physics one or something like that. So what I'm also telling you is, even if it's next class, after I do a zoom out, I'm going to zoom in and sort of over explain maybe each of the steps or tell you where I got them from. That will be super necessary and helpful for some people. Maybe it'll be annoying to other people. But but let me just warn you. First, I'm going to give you the skeleton of the whole thing. So I'm not assuming that you understand everything I'm writing right now. But you should flag where you have questions or what you need, because that will help us in the next class. Okay, so I'm going to write down some physics that you may or may not have seen recently. In fact, and this is what I mean by B. Like, what's the GDPs for 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 this problem? I think the GDP is, first in English, when all forces doing work on a system are conservative. I should have written this on there. Sorry, I'm not changing this. I'm just going to move it to the next. I'm moving to the next page. I'm running out of it. So B. So if you got A, then I'm just going to rewrite B on the next page. So don't worry about it. So B, when all, and this is a GDP. This is what I'm about to write now is a general concept. It is a law. It is like true. And it's technically true from classical mechanics from our last course. We've never said it before. I'm saying it now. When all, and you will know it, you might say it other ways or with equations and stuff, but when all forces doing work on a system are conservative, Okay, so first I'm saying this in English. Obviously, I'm going to write as an equation in a moment, but and every time I circled a word, it not only meant it was like or a phrase, whatever I'm circling, it's not only means it's important, but it also means that yes, I understand what we need. Like we might not know what we need a definition for it, which is where I'm going to I'll expand over the next couple of classes. But the concept I'm saying here is that if you have a system and all the forces doing work on that system are the kind of forces that we're ultimately going to call conservative forces, then the system will conserve. That means maintain. That means hold as a constant value the total mechanical energy. It means that the total mechanical energy of the system will be the same at any one place as it is at any other place. The amount of total mechanical energy will be the same at every single position for any system which is being worked on by only conservative forces. That's what I'm saying. Now, again, some of these terms have to be defined for this to be very clear. So I'm going to do that. But first, I'm going to just write everything I just said. I'm going to write it in the form of an equation now, which again will be more clear to some of you than others. But here's the equation form. Here. Okay, so B1 is the English. So B2, I'm just translating it into equations. Well, one second. Well, no, sorry. What I'm saying in short is that if all the forces doing work on a system are conservative, then the kinetic energy let me back up for a second. I'm saying, what do I mean by total mechanical energy? Total mechanical energy is defined to be all the kinetic, let me say it again, the total mechanical energy of a system at a particular point in space and time, the total mechanical energy of a system at a particular point in space and time is the total amount of kinetic energy the system has plus the total amount of potential energy a system has. Like literally, I'm saying this, that E, total mechanical energy, is defined to be kinetic plus potential. And the total amount of kinetic plus potential is something that is measured or computed for a given point in space and time. So what I'm saying right now is if we assume a system that all the forces that doing work are conservative, which is the case here, but I still haven't said what that meant. That means that if you know all the kinetic over here and you add all the potential over here and you add them together, then that total should be all the kinetic plus all the potential over somewhere else. Again, in the interest of time, I'm going to keep going and applying this specifically to this problem. But again, I actually understand that we need to like zoom in more on this and say exactly what it. If you were giving me homework and you gave me something that looked like some of this, that's what I'm looking for. So I'm going to go to step 4. Okay, so again, I'm saying things here that we'll go back and discuss, but just to give you the outline of the problem and the answer, what I'm saying here, so I'm saying in general, if all the forces doing work are conservative, all these things, work, conservative forces, all things that we will discuss. I brought like next class. But assuming this applies to this problem, which it does, I'm saying the total amount of energy over here of any one spot has to equal the total amount of energy at any other spot. Total amount of energy is kinetic plus potential. In this case, well, always kinetic is 1 FmV squared. I will explain why that is next class, but it's true. Kinetic energy is 1 FmV squared. Potential energy, that's a deeper concept that can differ from situation to situation. But in this case, in the case of a spring, potential energy, call it spring potential, the potential energy is coming from the spring. And the potential energy due to a spring is 1 FKX squared. So the total amount of 1 FmV squared plus 1 FKX squared over any one spot must equal the total amount of kinetic energy plus potential energy in any other spot. What are the two spots? Like, why am I coming up with two spots? The whole idea is anytime you use energy conservation, you are comparing one spot to another, one position, one point in space to another. And one point in space is a point in space where you have all the information, and the other point in space is the point of space where you're trying to solve for the information. Specifically, and you might want to put this in notes, although I'm definitely going to say it again, specifically, we use energy conservation when we know the speed at a certain spot and we want to know the speed at another spot. Or vice versa, we know the spot at a certain speed, so to speak, and we want to know the spot at the other speed. Like literally, you could put this in notes. I would recommend what energy conservation really is ultimately is a speed to spot correspondence. Like literally, that's what it is. The total amount of energy over here always has to equal the total amount of energy over there. So if you know the speed here, but you want to know the speed there, you can use, and you should use, energy conservation to find it out. This is particularly useful in cases where the forces and the accelerations are changing from spot to spot, so you can't use kinematics. So what are our two spots? Well, in this problem, the spot that we know about is the initial spot. We know where the mass was held originally, and we know how fast it was going originally because we were told. What we're solving for is the equilibrium. We know where the equilibrium is, but we're solving for how fast the thing is going at equilibrium. So those are my two spots. So even though, again, I'm saying, because we only have 3 minutes, I'm going to back up and expand on this next class, like where I'm getting this 1 FKX squared and all that. If you don't know where that's coming from, don't panic. But if you could follow the like macro logic of what I'm saying for the moment, if you could take, then we're just about to watch this. So here's, so my GD, or the thing we're using is 1 half mv squared plus 1 half kx squared over here at x equals 0 equals 1 half mv squared plus 1 half kx squared over here at x equals x naught. So remember I said before so we're going to plug in the numbers and we're going to get an answer, and then we're going to be done for today. But remember I recommended that you actually plug in numbers as late as possible in the game. So let's get in that habit. Like, first of all, and I'm going to do this fast because we're running out of time, but notice I've got a half in every single term. So I could factor out a half on each side and then divide each side by 1/2. In other words, because it's literally there in every single term, I could cancel out one. If we're only in some, I couldn't do this. If we're only in some of the terms, but since it's in every single one, I could factor it out and divide both sides by 1/2. But then furthermore, what am I solving for? I'm solving for V. I'm solving for V at x equals 0. Oh, sorry, before I even go, furthermore, let me like get rid of things to simplify this as much as I can before I plug in numbers. So at x equals 0, kx squared equals 0. Like if I plug in the zeros where I see them, so what I'm left with is, When I'm left with, and we're just about done, I know we're just about done in every way. Come on, come on, come on. Okay. So I have mv squared at x equals 0, like I'm equals 1/2 kx squared at x equals x naught, right? Like in other words, I crossed out this and I crossed out that. Well, oh, why did I cross out that? Because I know at x equals, I know we have 1 more minute. At x equals x naught, I know v equals 0 because I was told at the beginning of the problem. So I have this and this, right? Now, before I plug, oh, and the half is a mistake. Sorry, that 1/2 doesn't belong there. Okay. So I have this and this. Now you could plug in numbers now, but I recommend you don't. Get in the habit of not. What am I solving for? I'm solving for v. So I'm going to divide both. Just bear with me for 1 second. If you have to go. You'll get the PDF in a second. But if you bear with me, I'll be done in 1 second. I'm going to divide both sides by m because I'm looking for v. So I go like this. But I'm looking for v. So I square root both sides. So I say v equals this. And now I plug in numbers. And it's going to be a square root, so it's going to be, right? It's going to be like 200 times 0.15 squared all over 0.3. And when you do that, I'll do this fast. Of course, it's rounding because it's a square root, but you should get like 3.87 approximately meters per second. That's how fast the thing is going. And that's my step 5 at the equilibrium position. Notice it's very fast. It's much faster. And that's it. And I will hang out for a second if there's any questions. But of course, you go, but I'll upload all this, blah, 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 blah. But goodbye. You've been very lovely as usual. Just keep working. Okay. And so oh, Jadith has a great question. Hang on 1 second. Thank you, but I'm stopping.